Back in the day, machining metal meant dealing with an awful lot of noise and vibration. This is the Mill 390 damped milling cutter, and it's equipped with Silent Tools technology that's genuinely revolutionizing how we approach deep cavity milling. Now, what makes this tool so special? Well, inside that seemingly ordinary tool holder, there's a sophisticated damping system that absorbs vibrations before they can cause problems. Think of it like the shock absorbers in your car, but engineered to microscopic precision. The mechanism uses tuned mass dampers, basically weighted elements that counteract the natural frequencies that cause chatter during cutting. Watch how smoothly it cuts through this hardened steel. In the old days, you'd hear that telltale screech and see those chatter marks on the surface. Not anymore. The Silent Tools technology extends tool life by up to 50% compared to conventional cutters. And here's the kicker: it allows you to increase your cutting speeds by 30 to 40%. The insert geometry is precision ground with multiple cutting edges, and you'll notice how the coolant is directed right to the cutting zone through internal channels. This whole assembly can handle depths up to 8 times the diameter of the cutter, which opens up possibilities for machining deep pockets and cavities that used to require multiple setups and tool changes. This is drop forging at Dyrestall, and what you're watching is raw steel being transformed through controlled violence into precision components. The process starts with heating the steel billet to around 200 degrees Fahrenheit in those massive furnaces. At this temperature, the metal glows bright orange and becomes plastic enough to shape, but it still takes tremendous force to form it. That's where the drop hammer comes in, and this beast can deliver up to 5,000 pounds of striking force. Watch as the operator positions the glowing billet into the lower die. Those dies are precision machined to create the exact shape needed, and it often takes multiple strikes to achieve the final form. Each impact refines the grain structure of the metal, actually making it stronger than if it were machined from solid stock. Between strikes, you'll see the piece being rotated and repositioned. This ensures even material flow and proper filling of the die cavity. The whole dance requires tremendous skill, timing, positioning, and knowing exactly how many heats and strikes each piece needs. If you've spent any time around machine shops, you know the traditional way of making a complex part meant moving it from machine to machine, lathe to mill, to drill press to grinder. Each move meant new setups, new fixturing, and new opportunities for error to creep in. What Walter Tools is demonstrating here changes that entire paradigm. This is what we call complete machining or turn mill technology, and it represents one of the biggest advances in manufacturing efficiency in the past 30 years. Watch this multitasking machine center at work. It starts as a lathe, spinning the raw material while cutting tools shape the outside diameter. But here's where it gets interesting. Without removing the part from the machine, those same spindles that were turning the workpiece now become stationary, and powered cutting tools swing into action to mill flats, drill holes, and cut slots. The machine you're seeing has twin turrets, each equipped with both stationary and driven tools. This means operations that used to happen sequentially can now happen simultaneously. While one turret is turning the outside diameter on one end of the part, the other turret can be milling a hexagonal feature on the opposite end. The time savings are extraordinary. Let's talk about the tooling itself, because Walter has really thought this through. Those aren't just standard cutting tools randomly thrown into the turret. Each tool position is carefully selected based on the operation sequence. You've got turning inserts with chip-breaking geometries designed for the specific material being cut, drilling tools with through coolant capability to evacuate chips from deep holes, and milling cutters optimized for the interrupted cuts that happen in turn mill operations. The workpiece is held in a chuck that maintains micron-level accuracy throughout the entire process. And here's something that would have amazed machinists from a generation ago. The machine knows exactly where every surface is at every moment. Built-in probing systems measure critical dimensions during the process, and the CNC controller automatically adjusts tool offsets to compensate for tool wear or thermal growth. Watch as it drills those cross holes. The spindle orientation is precise to within a few arc seconds, ensuring those holes intersect exactly where they're supposed to. Then immediately it switches to a threading operation, cutting perfect threads in a single pass with a synchronized motion between the spindle and the cutting tool. The real beauty of this system is what we call one-and-done manufacturing. The part goes in as raw material, and it comes out complete, ready for quality inspection and assembly. No work-in-process inventory sitting around waiting for the next operation. No accumulation of handling errors from multiple setups. Now we're looking at something truly specialized: the manufacturing of containers designed to safely store radioactive waste for decades, maybe centuries. The stakes here couldn't be higher, and the processes you're seeing combine ancient forging techniques with cutting-edge welding technology. Instead of closed dies that form a specific shape, free forging uses flat or simple curved dies to manipulate large pieces of steel through multiple heating and forging cycles. That massive ingot you're seeing weighs several tons and has been heated to forging temperature in a specialized furnace that ensures even heat distribution throughout the entire mass. The forging press applies hundreds of tons of pressure, but watch how carefully the operators work the piece. They're not trying to form it in one hit. Instead, they're gradually working the steel, moving it incrementally, building up the walls of what will become the container body. This process does something remarkable to the steel's internal structure. It eliminates voids, refines the grain structure, and creates a material that's stronger and more reliable than cast or welded-only construction. Carbon steel alone isn't quite enough for radioactive waste containment. It needs a corrosion-resistant layer. That's where overlay welding comes in. You're watching an automated welding system depositing layer after layer of corrosion-resistant alloy onto the carbon steel substrate. This isn't just a coating. It's a metallurgically bonded layer that becomes part of the container itself. The welding process uses what's called submerged arc welding, where the arc burns beneath a blanket of granular flux. This protects the weld from atmospheric contamination and allows for very high deposition rates. Each pass overlaps the previous one by about 30%, ensuring complete coverage with no weak spots. The process is monitored constantly. Temperature, travel speed, wire feed rate, everything is controlled to ensure consistent, defect-free welds. Between welding passes, you'll notice they're letting the piece cool in a controlled manner. This prevents thermal stress and ensures the bond between the carbon steel and the overlay remains sound. The finished container will undergo rigorous testing, ultrasonic inspection, radiography, pressure testing, to verify it meets the exacting standards required for nuclear waste storage. What you're witnessing here is the Monroe system from BEMO, and it's brought remarkable precision to the world of steel stamping. The Monroe system uses a progressive die setup, which means the steel strip moves through multiple stations, each performing a specific operation. First station punches pilot holes for registration, second station might create the initial form, third station deepens the draw, fourth station pierces the final holes. And so on, until that flat steel has been transformed into a complex three-dimensional part. The press force is carefully controlled. Too little and you get incomplete forming, too much and you thin the material or even tear it. The BEMO system uses hydraulic cushions and nitrogen springs to control the metal flow during forming, ensuring consistent wall thickness and preventing wrinkles or splits. Now here's a machine that represents the pinnacle of precision in gear manufacturing, the Liebherr LC 380-500 gear hobbing machine. Hobbing is one of the most efficient ways to cut gears, and it's based on a brilliant principle. That cylindrical cutting tool you see, the hob, is essentially a hardened steel worm with cutting edges ground into it. As it rotates and feeds across the workpiece, it gradually generates the gear teeth through a continuous cutting action. The hob rotates at cutting speed while the gear blank rotates slowly in precise synchronization. The Liebherr CNC system maintains this relationship with extraordinary precision. We're talking accuracy measured in arc seconds. This particular machine can handle gears up to 500 millimeters in diameter and is capable of cutting module sizes that range from fine instrument gears to heavy industrial applications. What we're looking at here is industrial muscle on a scale that's hard to comprehend until you see it in person. This is a 4,000-ton press brake, and that 20-meter bed length means it can bend metal plates longer than a semi-truck trailer. This is the kind of equipment that builds the world's infrastructure: ship hulls, pressure vessels, massive structural components. The principle is straightforward. A punch descends into a die, bending the metal to a precise angle. But at this scale, everything becomes exponentially more complex. That 4,000 tons of force is distributed across the entire length through a sophisticated hydraulic system with multiple cylinders that must operate in perfect synchronization. If one end of the ram moves even slightly faster than the other, you'd get a twisted part instead of a clean bend. Watch how slowly and deliberately it moves. At this tonnage, there's tremendous stored energy in the hydraulic system, and everything is controlled with precision. The CNC back gauge you see positioning the plate is accurate to within a fraction of a millimeter across that entire 20-meter length. The tooling is equally impressive. Those aren't standard dies. They're massive steel forgings, precision ground, and often segmented, so different sections can be used for different bend configurations. For thick material, the dies might be heated to reduce spring back and achieve more accurate angles.